Hello and welcome back to Precalculus 1. There we go. Section 1.6 on transformation of functions. Transformation meaning we would like to graph a function that is shifted, reflected, flipped in some way, and we need to know those basic 6, 7, 8, whatever basic functions that we can move around. Functions that we play with in general would be, we said the constant function, that one you can shift up and down. And then you have the linear function, which was mx plus b. Then you have the quadratic polynomial function, that was the x squared. Then we have a cubic, that will have more forms when we hit the chapter 2. That's x cubed. Then we had the square root function. We had the absolute value. And they do have a cube root of x. Not sure why, but what the hell, we'll put it in. So these are the shapes. This is y equal some value c. It goes to c. So these are the basic shapes that I asked you to study. And off of these, I know which one is missing. 1 over x. Ha. Yeah, usually I never put the cube root of x. The book is pushing it, but yeah. But 1 over x is going to be used a lot in your Calc 1 class. So that's the one that you definitely want to know. All right, so what's common for all of these functions is y equals f of x. They all go in the same bag. You stuff them all in the same bag, and you just call them f of x. That's it. And now, when we learn transformations, we learn transformation as applied to a function, and we apply it the same way to each one of these graphs. So you're learning 1 through 6 or 7, 6 transformations, but whatever transformation you learn, it applies to each of the functions. By the end of the course, we'll add exponential and logarithmic to this. When you go to Precalc 2, there will be 12 trig functions, 6 basic and 6 inverse, right? So you will add another 12. You go to Precalculus, you will add, to calculus, you will add hyperbolic functions and so on. Doesn't matter what function you're looking for, even those that you might not see until graduate school if you go to. They all obey the same rules. The first rule is going to be vertical shift. And that one you get when you take a function and then you add and subtract c. That was a $20 a guess right there. For no reason. Unless it got stuck in mud and had to come out. Then it's justified. So now, vertical shift. Words. Vertical. The function goes up or down, right? That's it. Up or down. I generally like to put the arrow like this, meaning goes up or down, depending on what you have. Positive c is going to ship it up. Negative c is going to ship it down. The amount of units given within C. So let's take a look at an example here. I can have y equals x squared plus 2. The way this works is you draw the default function or the parenting function, whatever you want to call it. You draw that one. You can use dashed line if you want to. So this is the parabola. Which is the x squared. Now I need to take the same line and bring it 2 units up and draw the same shape. And we're done. So it's going through 2. Let's say you have y equals square root of x minus 3. You will draw square root of x dotted. That's your square root of x. If you are using 2 colors, go ahead, use 2 colors. Maybe I should switch to 2 colors. Now, I need the same line 3 units down. This 0, 0 goes 1, 2, 3 units down. And then I just have the same shape. This is root x minus 3. So this is what we are learning now. We are learning that vertical shift would simply move the graph from its original state up or down whatever amount of units you have. Now you're going to say, wait, what's my original what is my original shape? Memorize it. That's why this is called part what you study, right? You study that these are your basic shapes, and you go from there, and then you start moving these up, down, left, right, and reflections and a whole bunch of stuff we're going to learn. So knowing the basic shapes and then move those around. So vertical shift is what you see right now. If you add or subtract the value at the end of the function, right, to add and subtract the value to a function, that value will move the whole function up or down. Next one is horizontal shift. So what is that one? Beautiful. Left and right. So now we are going to put this as f of x plus minus c. You see, now you're not adding a number to the entire function like before. You are adding plus and minus number directly to each x in the problem. So that's going to be a left and right shift. It's positive c shift left, negative c shift right. It's part you learn. Now, before I do any examples, I need you to see the difference. Y equals square root of x. Y equals square root of x plus 2. Y equals square root of x plus 2. This is a shift up plus 2. This is a shift left 2 units. Do you see how the plus 2 is in under the root? Do we see that? Another example. Y equals 1 over x. Y equals 1 over x plus 3. Y equals 1 over x plus 3. This one is up 3, units. This one is left 3 units. You see that the plus 3 is in a different location. The up and down shifts we learned are added to the end of the function on the outside, right? Where the new horizontal shift we are learning is added within the function. So this is inside the square root. It is inside the fraction. And that's how they're different. So now, if I want to graph this one, I will take the original square root of x and then move it 2 units to the left. So from 0 to -2 and draw the same shape, and that's my root x plus 2 in the root. It shifted left because we added a value directly to x. Yes?
Why did it shift left? Because it's plus 2.
Well, it's okay. It's the plus and minus the vertical shift is backwards.
Okay.
But it sounds okay because plus went up. It's actually plus should go down, but because it's on the opposite side of the equation. I can't show that right now because we have to learn something else, but I can prove that this is okay. All right, I can prove that this is okay. Plug in a value of 0 in this function. If you plug in a value of 0, you will have a square root of 2, which is this value here. If you plug in a -2 for that x, which is this value, well, -2 plus 2 is 0, and square root of 0 is 0. So you see that the y value of this point is 0. So it works.
Okay.
Well, I can talk about it. Technically, y equals f of x is the function. And then if you have y plus minus c equals fx plus minus, let's say, k, once you move this c to the other side, it would be minus plus c. You see how they're opposite signs? So if you want the whole thing to have opposite signs, then keeping it on this side with the y, plus would be down, minus would be up. But when you move plus c to the other side, it becomes minus c. And when you move the negative c, it becomes plus c. And then it's plus with the up. And so it's a little bit confusing right now. So that's why I want to hold off on these kind of things. In general, students memorize that up and down, so plus c puts me up, minus c puts me down. That's for the vertical. Horizontal shift plus c puts me left, and minus c puts me to the right. Now you say that's opposite, but as I said, technically this is opposite because plus is supposed to go down, but yeah. So we'll deal with that when we go to chapter 2, when I have equations that I can use to explain this better. Right now, it's more of a memorizing that you have those 6 graphs to memorize if you don't know them already. And then that these shifts move things around. Let's take a look at this one. 1 over x is the line like this. And that's 1 over x basic. And then plus 3 shifts everything to the left 3 units. So we will draw this vertical line called vertical asymptote. And then we're going to draw the same function. And now this function is 1 over x plus 3. Those are two examples. Now, this is your original y-axis. This is your original x-axis. The dashed function here is 1 over x. And the solid one is the 1 over x plus 3.
Could you explain that one more time?
Yes. Now I can use different colors too. I'll erase this. So what I have is I have 1 over x versus 1 over x plus 3. So 1 over x is the one we memorize. We don't get to debate this. This is something that you learn. And if you don't know it, you have to pick points and make this graph. So this is the default basic function. So, and I use the black color for that one. And now the plus 3, as you can see, is not attached to the whole function. It's attached only to x, which means left 3. If this is at 0, I'm going to go 1, 2, 3 to the left and put this barrier, which is technically the new y-axis. So this is the original y-axis. That's where the y-axis is. And now I am shifting the whole graph to the left. So the whole thing moves to the left. Well, I'm keeping the same shape, so I'm going to draw the 1 over x plus 3. And that is now shifted to the left. 3 units. Better?
Yeah.
Because I'm going to do one more now. Let's take a look at a function that has two shifts combined. Say y equals absolute value of x minus 2 plus 3. So this one has two shifts. It has 2 right and 3 up. See, the 2 is attached directly to x, which means it's a shift left-right, but because it's a minus, it's a shift to the right. This is what we are learning now. So don't panic if you don't know it. You haven't learned it yet, right? We are learning that right now. So pay attention to the new concepts.
So that would mean that you would have to include both types of shifts when you're graphing the second function.
Perfect. And we can do that in one step at a time, which is why I, on the exam, provide 6 boxes. First box will always have the parent function, the default one, and then you take that one and keep evolving it through stages. And then sometimes you have 2, sometimes you have 3 transformations, sometimes 5, right? You will evolve through boxes, and sometimes you use up 2 or 3 or 4 boxes, depending on your. I will give you 6 boxes on the test. They will look like something like this, right? And they will all have the grids inside. And then you will go and you say, oh, the basic function is the V shape, so you draw that on the first, and you just say that's absolute x. I'm going to do this much nicer. And then you move it, and you move it, and then you're done. So let's do this. I don't need boxes now, but on the test I will provide you with boxes and graph, so you can do better graphs. So the first stage here is to draw the parenting function, default function, whatever you want to call it, which is our absolute x. That's it. Y equal absolute x is the basic function. Then we can move it 2 units to the right. So we are now going to take the same v, but we are moving the origin. So now we're going to have this. And that's a 2. And this is y equals x minus 2 in absolute values. So I hope you see that it evolved. And now the final one is to move everything 3 units up. So we already moved 2. Now we go 1, 2, 3 up. And we draw our final shape. And if you are interested in full credit, you have to label this as 2, 3, this point. Otherwise, you don't worry about the credit, don't worry about it, right? But if you want that point to label if you want the points for labeling everything, you have to label 2, 3. Yes?
So when you put the paragraph in the one that you made together, like how you were graphing all the other ones, you're putting them like in the same.
The answer is yes, and most people do that. When you have multiple transformations on one, I like to separate them so you can see the progression, okay? Because it becomes very busy with lines. And, let me write this. This is absolute x minus 2 plus 3. If I am to do this problem on the same graph paper, I'm going to erase this, but I just want to show what this would look like. It would look like this, and it would look like that. Like that's what if I used one only, if I just had this, it would be that busy, right? So I do the basic graph, and then one transformation, another transformation, and then the graph on the bottom is the answer. Let's take a look at one more of these, and then we'll do the next set of transformations. So far, we learned 2 out of 6. We learned horizontal and vertical shifts. That's 2 out of 6, right? So let's do one more example of them combined. And try this one on your own, and then I will work out the problem. So let's go with y equals square root of x minus 3 minus 1. So we have 2 transformations. That means you will draw 3 graphs. The basic parent graph on the first, and then 2 graphs where it evolves, third graph being the last. Is that a weed whacker or a truck? what is our basic function?
Y equals x, square root of x.
Beautiful. And that is just this squiggle, right? And then what should I do to it? Move to the right. How many units? 3 units. Perfect. So this point here is where the function starts. That's the point that goes left, right, up, down. So we are going to go 1, 2, and land at 3 and draw the same shape. That's it. And this is now y equals square root of x minus 3. And now what should I do? Move down 1. So I go 1, 2, 3, go down 1, draw the same shape. Now we label this as 3, negative 1. That's if you want full credit, otherwise don't worry about it. X minus 3, and then minus 1 on the outside, and that is this over here is our answer. That's the final stage, right? We had 2 transformations, 2 shifts, and that will be the end. Cool? The next 2 transformations are a little bit hard to see on functions we study in Precalc1. They are amazing in Precalc2. The book actually uses those functions to show the shift. They actually use trigonometric functions to show horizontal stretching and shrinking and vertical stretching or shrinking. So let's go with vertical stretch slash shrink. Now that happens when you multiply a function by a number. So c times f of x. Now this one is kind of hard to spot. I mean, if you graph a couple of these functions together, it does show. Generally what we do is we use trigonometric functions to show it off. It's not humanly possible to do the greatest possible job here on Precalc1 functions, which is why we use trig. Even the book is using sine x without telling you it's sine x. They just say, oh, let this be some f of x line, which is actually sine x from trig. So for vertical stretch or vertical shrink, what's happening is you have some function, and this is, again, the book doesn't tell you, but I will because I'm that awesome. This function is called sine x, which is Precalc2. It's a trig function. Sine x. Now this is what I'm going to do. I'm going to make a larger peak, but hit the same nodes. And I'm going to call this 2 sine x. So when I multiply by a number bigger than 1, I make the function bigger, and this is how we model waves. You know the sea waves, and you throw a pebble in a pond or a brick in a pond, right? Or you jump into a pond. The side, if you cut the water on the side and you look at the wave, right? Depending whether you tossed a pebble or a brick, you're going to have a black or a red line. And now I am going to do the shrink in blue I'm going to go halfway through, and I'm still going to go through the same nodes. And the blue one I'm going to call 1/2 sine x. Now in a book they tell you 2f of x, half f of x, because they're avoiding to say sine, because I guess it's sin to talk about it in Precalculus1, right? So that's the vertical stretching or vertical shrink. Very hard to spot in Precalculus1. I can actually draw some of the square root function. I mean, you can see it, but the trig is the best. Here is an example of square root of x, the black line. It's a square root of x. And then the red line, 2 square root of x. And the blue line, half square root of x. Because what you are doing is every y value of the black function gets either times 2 or divided by 2. Absolute value, which is at 45, would go in for 2 absolute x, and then would go like this for half absolute x. So what the number, when you multiply a function by a number, it makes it grow, what we say in amplitude, or it shrinks it. Now, when you draw these things, you just eye them. This is something that you can get ahead with for, let's say, calculus graphing. Here is the typical y equals 3 over x minus 5 formula that you might run into calculus. You need to graph this so you can check increasing, decreasing, a whole bunch of other stuff. What's the basic function here? Yes, what is it? Rational function, what's y equals? Just 1 over x, beautiful. So we are going to start by just drawing out 1 over x. Then the next thing we're going to do is we're going to shift this 5 units to the right. So 1, 2, 3, 4, at 5 units we are going to draw this vertical asymptote. And now we draw this, and this is 1 over x minus 5, because we shifted everything 5 units. Now, I will write here just in case. This is 3 times 1 over x minus 5. So you see how it is actually, that's that vertical stretch, right? So it should make it taller. But this 1 over x already goes to infinity. So it's very difficult to pull that off on a graph. You know what it's going to do? Times 3. It's going to just make this line like that and make this line like this, and that's going to be 3 over x minus 5. Yes? I'm sorry?
That's the graph shifting when you multiply by 3?
Yes, the blue one. Now, as I said, it's not humanly possible to do amazing here. But hold on. We're in 2020 today. What I just did is I gave you the way we used to teach this in 1700s and 1800s and 1900s. Today, you have internet. And if you want to learn this, you go to a website called Desmos, which is what graphs functions. And you learn graphing like nothing. Now let me show you what you can do on Desmos. Beautiful free math. Start graphing. Done. Over here, you want to explore the graph square root. If you type SQRT, it types the square root for you of x. And that's it. That's the only thing you want. Clearly you see the red line we have been talking about, and you have the red color in front of the root x. Now, in the second function, I am going to go SQRT x minus 5. X minus 5. Do we all see the blue line? Does it start at 5? It's clearly the shift to the right 5 units. Next function, SQRT x, then you push the arrow to escape the square root, and you say minus 3. You have the green on the green color corresponds to the green graph, and you see that it went 3 units down because it starts -3, which is between -2 and -4. With this tool, sit down for an hour or two on multiple days, spend 30 minutes today, 30 minutes tomorrow. You keep plugging the functions, and you see that every time when you modify x directly, the graph will go left and right. Every time you modify the entire function by adding or subtracting a number, it will go up and down. Now, this is not what I wanted to show because you understood that very well. So I'm going to kill these and then go here and say 3 times SQRT of x. Do you see what happened? The black graph now is still somewhat the same shape, but it's rising faster. How about we go and we say 1/2, which is 0.5 SQRT of x. Why did you give me red again? It's the redder red, okay? I just killed it. How did you change it? There's no changing.
Hit the cog symbol in the top right, next to the 2 arrows.
Next to the 2 arrows.
Yeah.
Oh. Let's go. We don't have enough purple in life. There we go. Purple. Thank you. So purple. And all of these functions now, so hopefully it starts making sense that it is a vertical stretch or a vertical shrink, because what it takes the basic function and then stretches it up or stretches it down. Now we had questions about 1 over x. It's time for us to look at 1 divided by x. And we get this function, which we memorized what it looks like from the basic shape of functions. Really? Relax. There we go. Holy nightmare. Now, I'm going to multiply 1 over x by 3. Well, that's just 3 over x. You see what it did? It creates the blue line. And now, if I multiply by 1/2, it will be 1 divided by 2x. That's the green line inside. You can learn all of these without me, without book, without anything, observing the patterns of what's happening with graphs as you plug one of the values in. Now, it's not going to be 5 minutes because you have 6, 7 different functions to worry about. You have absolute x, you have square root of x, 1 over x, x squared, right? So you will play with all of those and try and get what they are. So here's x squared, 3x squared. That's the black one. And then we can do half x squared, which is going to open wider because it's, instead of stretching it up, it shrinks it. So when you squish the purple a little bit, it kind of opens out more. So half 0.5 of x squared is the red one, and you see it's a little bit relaxed. You use Desmos to practice these shifts and so on, and you can graph things to learn what they look like as you go. Now, we are also going to have, so that was a vertical stretch and shrink. We also have horizontal stretch and shrink. And that one is when you multiply x inside the function. So now we have f of x versus f of cx, which is horizontal, versus cf of x, which is vertical, which is the one we did before. So now when the number is inside, it's going to shrink or stretch horizontally. Again, the best function for this would be trigonometric function sine. It makes waves faster or slower. So if this is my original sine x, I can make that twice as fast using sine 2x. Eventually, this precalculus might manifest in your life as physics, and you learn waves, and you learn that this is twice as fast. Or we can go slow kind of hard to hit. There we go. If we go slow like this, that's sine half x multiplied by a half. So you can also compress them or stretch them depending on what you do with which number you take. Is it a more than 1 or less than 1? If it's more than 1, then clearly you are stretching. Well, in this case, it looks like a compression, but it's twice as fast. And the numbers less than 1, they make everything slower, so it looks like more stretched. Now, unfortunately for our Precalculus1 functions, these effects look the same as the effects of the previous transformation. And that's why it's not that great to use square root of x and all of these kind of things. Here is something that you guys hopefully understand. Look, if my f of x is square root of x, and that's my basic function like this, right? So we beat this one to death. What is going to happen if I have f of x equals 2 square root of x? Well, that was the old transformation. What happens? Yeah, so it's a vertical stretch, so it's going to go faster up, right? So this is my old root x, and then it's just going to do this. And that's 2 root x. Now, f of x equals square root of 4x. What is that going to do? No, that would be x plus 4. X plus 4 would move it to the left. But this is 4 times x. Horizontal, right? Yes. Yes. I'm going to take both words. Fine. The answer is yes. But what's the square root of 4? Do you see how this thing is exactly the same as the previous one? So Precalc1 functions are not the best ones to explain this, okay? That's why I went and I used the sign earlier. Because it appears that it's the same transformation. It's not, right? But they are equivalent for square root of x. They are not equivalent for trig. So it's kind of hard to see these kind of things. You can do the same thing for absolute value. It would do the same. If you have 4 absolute x or absolute x or absolute of 4x, that 4 can just jump outside. So it's very hard to understand this particular, which is why I usually don't bother students with this particular transformation a lot, because it's so hard to understand this transformation on the functions that don't utilize this transformation very well. But for trig function, it's absolutely clear whether you are stretching it up or you're stretching it forward. And they're not interchangeable like they are for most of these. So that's something that you can also explore this in Desmos, clearly. We are going to take a look at good old square root of x. SQRT of x. 2 SQRT of x. And SQRT, I'll put 2x. You see that? It kind of does the same thing over and over and over again. You can't really tell because the Precalc1 functions are not greatest for this type of a problem. But that's okay. You will make that up in Precalc2 when the only functions you deal with are trig functions. So I won't bother you too much with horizontal stretching and shifting. But then I promise to make it up to you in Precalc if I teach it, right? I promise to make it up there. One more type of transformations and the lecture is over. These transformations are called reflections, and that's just minus signs that pop in to reflect the function on either x or the y-axis. So the last set of transformations are reflections. And we have two reflections. We have negative f of x and we have f of negative x. And that completes our list of 6 transformations which every function that exists has. Now let's take a look at these. If I have f of x equal square root of x, then I'm going to have f of x equals negative square root of x, and finally f of x equals square root of negative x, like that. So these are the basic function, which is our parenting function. Starts at 0, 0 and goes wee, like that. So this is our square root of x, seen it many times. What is happening with the other graphs? Well, the minus sign in front of the function, no matter what function you can have 1 over x, you can have x squared. The minus sign in front is going to make the reflection on x-axis, so this graph is going to go below now x-axis. So x-axis reflection. And the last one is going to be y-axis reflection, so it's going to look like this. Y-axis reflection. So that's your first example. I used this property today in differential equations, which is calculus 4. I used this property today of reflection because I had to transport one of the functions that had the negative x. We will learn that function in chapter 3, exponential function. So I had this and I needed that. So that's clearly this transformation here. I used that today in that class, and it's going to be around for the rest of your math education. So now what do? Let's say we have y equals absolute x, y equals absolute negative x, y equals negative absolute x. The basic function is the one that goes 45 degrees like that, both sides, and we leave it alone. What is happening on the next one?
Just like the same thing.
Exactly. Very good. It's exactly the same thing, because the absolute value will just kill that negative. So the graph won't change at all. Same as the previous one. But how about the third one? Flips, what do you mean? Not the y. The x-axis flip.
Oh,
So it's going to go, whee.
yes.
That's what you meant.
That's what I was thinking in my head.
Oh, you said, okay, this is what you said. You said the function is hugging y-axis, so let it hug below.
It would make, it would be like
Okay.
flip this way, but now I understand.
Sure, it's an x-axis reflection. You're looking where the mirror is, right? And the mirror is on the x-axis in this case. But yeah, okay. So you were right. It's just it didn't come. It didn't translate.
I was thinking it in a different way of thinking, but
Okay.
you're right in theory. Yeah, in theory. I would have drawn it correctly on the test.
Yes. Yeah, I can't. It's as long as it's right over there, because I can't really go inside the mind.
Yeah, as long as I get the right answer, it doesn't matter.
Yeah. Whatever it makes sense. So now we see that, you see that negative in front of the whole function can shift everything down. So that's another one of. And now I would like to spend 2 seconds here and examine what is happening with the number x equals positive 2 in all of these cases. When I plug in x equals positive 2, which is right here, it will return positive 2 answer. Make sense? Right? What happens when I plug in positive 2 on the other one? Same. But what happens if you calculate? It will be absolute of negative 2, and that's still 2, right? So I still get the 2 back. Cool, huh? Of course, math. Now, what's happening in a third one when I have negative of 2? So when I plug in 2, well, absolute value of 2 is 2, so it's negative 2. And you can see it on the graph that it's negative 2. Right? That's negative 2 on y. It has to match. It has to match in calculation. It has to match on a graph. Right? That's where the math, and there are no exceptions. Right? No exceptions. Either way, whether it's graphical solution or you are calculating by hand, if you are using 2 in each one of these to check, you will see that you are getting correct answers. So sometimes when you're not sure which way the graph goes, you can just kind of test one point and see. That will give you the y value, and just make sure you snake your graph through that point, and you're good to go. Good. Now, they say order of transformations, and they tell you which one to do first and second and so on, and this order is just wrong. The first one you want to do when you have multiple transformations is always reflection. Please always reflect first. You don't have to worry about stretching. They say stretching. They say horizontal shifting, then stretching, then reflecting, then vertical shifting. Hell no. Hell no. We are going to do reflection first. Reflection first, then your shifts, and you don't have to even worry about stretching, right? Because it's not humanly possible to do the great job on stretching in Precalculus 1. I told you that. And I promise to make it up to you in Precalc 2. With trig, I'll kill you with vertical and horizontal stretches, okay? Because it's insanely important for trig. So, we reflect first and then shift. And if you want to stretch it, then stretch, like make it go, faster or slower, depending on whether you have a whole number or a fraction. So here we go. Order, reflect, shift, stretch. Stretch, shrink. This is the order that will not fail you. The problems can be tricky. So here we go. Y equals negative 2 square root of x plus 3 minus 1. This one has it all. Almost all. Where do I begin? I begin with identifying all of the transformations that I have, and I just put like a list, table of all of those shifts. The same problem you guys are solving when you want to go somewhere. Step number 1, approach your car. Step number 2, unlock the car. Step number 3, open the door. Step number 4, sit. Step number 5, close the door. Step number 6, put the seatbelt on. Step number 7, start the car. right? It's a step of the procedure. Can you really? Well, you can start the car without getting in. Yeah, if you have a remote starter. But the trick is that for most people, and those definitely without remote starter, you can't start the car until you're already in. Now, some people start the car first and then put the seatbelt, which is by safety regulations not supposed to be done, because you don't know if the car is going to jerk and flip you in a ditch, right? And you don't have the seatbelt yet. It's a machine, right? So there are reasons why seatbelt first, then start the car, right? So there is a set list of steps to start driving. There is also a step before you unlock the car, which is walk once around the car to make sure that all 4 tires are okay. Depending on what kind of person you are, someone might have slashed your tires, okay? Also, you want to check if there is a boot on your tire or not, because maybe you illegally parked and you didn't even know, and they just came in and put a boot on your car. You didn't see it approaching the car because it was on the other side of the car, and then you sit in your car, try to drive, and the car is not getting anywhere. You might even damage your car, right? So there is also the step of actually approach your vehicle, walk around the vehicle once to make sure that there is nothing impairing the vehicle, then get in, then do all of the other steps, right? So now, when I have this, I'm going to use the same mental picture to get this problem solved. Number one thing is for me to write the step, all of the things that I have. Reflection, stretch, no, that's a left, 3, down, 1. You can also write a list or like a table of these things on a side. If you organize it any way you want, just have a clear picture that each one of these does something. And now we can build our function, right, in those boxes which I mentioned before. The parenting function here is square root of x. So that's y equals square root of x. There will be a line on which you get to write what is the function on the picture. Now, I did ask you to do reflection next, so you don't have to worry about reflections. Now, this is minus applied to the whole function, which means is it x or y reflection? X. Very good. Which means the graph is going to dip below x-axis. What happened there? So we're starting at 0, and we're just going to draw this, and this is my y equals negative root x. The next order of business is to move it left, right, up, down, whatever we need. Those vertical, horizontal shifts you can do in any order you want. So I just want all the reflections to be done first. I suggest, do whatever the hell you want, all right? I suggest reflections first, shifts, and then even if you don't have a stretch, can't care less. So here we go. The next one is left 3. So this is going to be my negative root x plus 3. Then I have down 1. So I have to go to my negative 3. 1, 2, negative 3, and put down 1. And I draw the same shape. And I label this point as negative 3, negative 1, because I want full credit. Right? Otherwise, don't worry about it. And this is my negative root x plus 3 minus 1. So I did this, and I did this. The only thing is to stretch it 2. That means make it drop faster. That's all it is. So for the final graph, and in this case it's a picture number 5, I am going to go to the same -3, -1, and instead of dropping it like this, I'm going to drop it faster. Again, not humanly possible to do. Amazing job there. So it's okay. And that one there is the graph function by hand. So I have -2 square root of x plus 3 minus 1. And that last graph is the answer. The author of the book really wants you to know this stuff. What you see on the first page are 32 problems of homework listed in this little sliver, right, of page. Like this is what? A fifth of a page? Has 32 problems for you to try. Look what happens when you flip the page. Another 130 problems, another 100 problems for a total of 130 problems to practice. I can't stress how insanely important this is. In calculus courses at RVCC, you do not have graphing calculator. If you cannot graph in a lot of problems, you are doomed. My Calculus 2 course, which I am teaching tomorrow, is utilizing these techniques to create graphs for the formulas and stuff that they graph. If you are not able to sketch the functions, you cannot set up problems. You see what do you see here? This is a precalculus, right? Is it? What do I have here? You all know how to graph this. Absolute x shifted 9 to the right. This is a Calc 2. It's 4 courses from here. Precalc1, Precalc2, Calc1, Calc2, right? There it is. 0, 0, 9 units, and I have that. And then I have x over 2, which is a linear line, goes through the origin. That's the blue one. And now I have the intersection of this, and then how calculus happens. If you don't know graphing, and you have no access on the graphing calculator, your grade on the first Calc 2 exam is 15 at best, right? On partial credit for the stuff for knowing formulas and things like that. You simply cannot graph. And if you cannot graph, you cannot solve the problem, because the problem says function on the top minus function on the bottom. Well, without the graph, you don't know which function is on top, which function is on the bottom. If you're looking at this, any pre-calculus student will say that linear line was on top and the absolute one was on the bottom. And that's exactly what you have seen in that integral. Don't worry about what the integral, but I'm saying that this is the graphing part. Two parabolas, minus x squared that opens downward, minus x squared. X squared, and then you reflect it, minus x squared, it opens down. So minus x squared is looking downward, positive x squared is looking up, and then you have top minus bottom to do calculus later on. This course is called Precalc, and as I said, sections 1.6, 1.7, and 1.8 will be the sections that you will be using a lot in all of your courses coming up, right? And we are going to repeat these sections when we jump into chapter 3 for exponential functions and logarithmic functions, to graph those and shift them around left, right, up, and right, reflect. So once we get in the chapter 3 and learn those functions, we are going to use the same methods to flip them. Here is your 3.2 homework, and you can see in the corner that some of these lines are looking up, right? Some of the lines are looking down because they are reflected, and that's just a negative sign, just like we had in our course here. So please make sure that you do, if you can, double the homework for 1.6 because you really need to know these things. Now, you only have basic and scientific calculators on exams. Now, if you go to four-year schools like Rutgers, NGIT, and so on to take calculus there's no calculator, period, of any kind on any class, any exam, or any assignment. They have zero. Virginia Tech as well, and many other four-year schools do not allow any kind of calculator in any of the math courses, right? So learning to graph, guys, is essential for your future survival. So on Wednesday, we will be, they changed the picture. We will be learning 1.7. So we'll deal with that on